Okay, now we're going to jump across the periodic table. So we had dealt with group 1 and group 2. Now we're going to go all over here to group 17, also known as group 7a. Okay, these are the halogens. Okay, and when we talk about their valence configuration, they're going to be 2s2, 2p5, or 3s2, 3p5, and so on. Notice that I don't have a 1s2, 1p, whatever, because the first energy level doesn't have a p block, right? Or doesn't have a p sublevel. So it's going to start, all halogens are in the second energy level and below. They also have 7 valence electrons, because if we add up the s and the p sublevels, it's 2 plus 5, gives us 7. Okay. They are very reactive nonmetals, so extremely reactive. They're nonmetals because they're to the right of the staircase. Most of them are diatomic. Diatomic means that if they show up by themselves, for instance fluorine, if you were just to have pure fluorine gas, the fluorine atoms could not travel on their own. They would pair up and they'd make it F2. Chlorine is also one. Bromine is also another diatomic. And then iodine. The only halogen that is not a diatomic is astatine, which is all the way at the bottom. Now their name, halogen, turns out halo is actually the prefix for salt, and then gen, think that it generates. So it's a salt generator or a salt former. One example would be sodium chloride, which is the classic just table salt, which is made up of sodium, which is a group 1 metal, combined with chlorine, which is a halogen. Okay. In terms of the 3 trends, radii, ionization, and electronegativity, they are the opposite of group 1. So group 1 was extremely large. These are the big atoms. Group 17, these atoms are very small, very tiny atoms. That means that their electrons are very close to the nucleus, so they have high ionization energy. Their positive nucleus is going to hold tight to their electrons, so they hold very tight to their electrons. It's very hard to remove the electrons from a halogen. Okay, and then in terms of electronegativity, that is also very large, so they have a high attraction for electrons. They love to pick up new electrons. So alright, so kind of the opposite of group 1. Group 1 was big, didn't care about its electrons. Halogens, on the other hand, very tiny, and they love electrons. They don't want to lose the ones they have, and in fact they love to gain electrons. Makes sense because they're right next to the noble gases. So if they just gain 1 electron, right? So they gain 1 electron, all of a sudden they have their octet. So these guys, our halogens, are typically going to form a charge of -1 because they want to gain 1 electron to get that octet. Okay, and then just to talk about my picture down here, these are 3 examples of halogens. You have chlorine, you have bromine, and you have iodine. Notice that chlorine is a gas at room temp, bromine's a liquid, and iodine is a solid. So halogens vary in terms of their physical properties, but chemically they behave very similarly. Now the last major group that I want to talk about is the last group on the periodic table. So we're talking about group 18 or 8a. Okay, remember these numbers with the A after them, they coincide to the valence number. So noble gases have 8 valence electrons. Their configuration would be ns2, np6, so that means 2s2, 2p6, or 3s2, 3p6, and so on. There is one exception. It is a noble gas, but it won't have this configuration. That exception is right here. This is helium. Now the thing about helium is it's in the first energy level. The first energy level does not have a p sublevel. So the only thing it has is the s. So the configuration for helium is just 1s2. Okay. However, for helium, it doesn't really need a true octet of 8 electrons. Just having 2 in the 1s is enough to consider it an octet. Okay, so for helium, an octet is just 2 electrons. Now, because all of the noble gases have a full octet, that means that they are non-reactive, so they're stable, right? And fancy name for that would be inert. They don't want to gain electrons, they don't want to lose electrons, they're happy just the way they are. In terms of the 3 trends, noble gases are tiny, okay? Extremely small, they're all the way here at the far right. So helium itself is a super tiny atom. Okay, very, very tiny. In terms of ionization energy, they have the largest ionization energy. They are stable, they are inert, they're happy, so they do not want to lose their electrons. Okay, so super hard to remove electrons. Okay, it's just not going to happen. Huge energy, huge amounts of energy to pull these electrons off. In terms of electronegativity, though, this is the first time where we see the ionization not match up to the electronegativity. Okay, in fact, we don't even consider electronegativity for the noble gases. And the reason why is that noble gases, again, have their octet. They're happy. Electronegativity is saying, how well do they attract electrons? No, they don't attract electrons because they have their 8. They're happy with their 8 electrons. They don't need any more. So they don't have electronegativity, or we don't consider it. Okay. Now, the question I usually get is, okay, you talked about those groups. What about the stuff in the middle? Well, that would be the D and the F blocks. So the D block, the middle of the periodic table, is known as the transition metals. It's going to include things like iron and gold and silver and manganese and vanadium and cobalt and so on. Okay, those are all transition metals. They have their electrons in the D sublevel. Okay, then the F block would be the rare earth metals. So it's going to be things like uranium, okay, and other rare earth metals. Some of the metals in the F block actually are man-made only, and a lot of them actually are radioactive. So those are the rare earth metals. That's pretty much all you need to know. Okay, they're metallic, they're reactive. This part here you do not need to know. Okay, the S and the D and the S and the F and all that. Don't need to know that. Okay, for D and F blocks, I will not ask you how many valence electrons they have. We will talk about how many electrons they've gained or lost to become an ion, but I'll teach you how to do that later on. Okay, so for right now, this is all you need to know about them. Don't worry about anything else. The only thing we care about when we're talking about valence is the S sublevel plus the P sublevel. Okay. Alright, so that is the end of our video. Make sure that you complete your whisk. Make sure that you create your hot question. That means that you're asking a question about something in this video that you're confused about, or you're creating a question that would be a good quiz or test question. Okay, we'll see you guys. Have a great night, and we'll see you in the morning.